So now that we have these drawn in 3 dimensions and we figured out if they are polar or non-polar molecules, we can go ahead and figure out what intermolecular forces, or IMFs, are available to the molecules. So remember, an intermolecular force is a force between the molecules. So if I have another carbon dioxide next to this carbon dioxide, there is a force of attraction between these two molecules, not within the molecule. Okay, that's intramolecular forces when we're talking about the bonds. Intermolecular forces are between molecules. So because carbon dioxide is a non-polar molecule, as distinguished when we figured out that it has polar bonds, but they cancel each other out, therefore it's a non-polar molecule. So non-polar molecules only have dispersion, or London dispersion, or van der Waals, whichever way you're describing them. Usually chemists call them dispersion or London dispersion forces, but sometimes people call them van der Waals forces. Okay, so dispersion, that's the only intermolecular force for carbon dioxide. So that's my little dash, dash, dash lines here. So if I have another carbon dioxide, it's attracted to this carbon dioxide just through one force. That's it, dispersion force, which is a very weak intermolecular force. So when we boil carbon dioxide, we're breaking the intermolecular force, which allows each molecule to be an individual molecule floating away as a gas, which of course at room temperature, carbon dioxide is already boiled because it's in a gas state at room temperature. Okay, water is a totally different case because water is a polar molecule. Okay, so polar molecules are attracted to other polar molecules through dispersion forces, because everything has dispersion forces, so we always list that one, but also through dipole-dipole forces. So dipole-dipole forces are available for polar molecules. So since water is a polar molecule, remember that was distinguished by the fact that it has oxygen, the central atom, has 2 bonding pairs, 2 lone pairs, and it is in a bent shape, and these 2 polar bonds do not cancel each other out, therefore it is a polar molecule. Okay, so it has dispersion, it has dipole-dipole, and it also has a third force called hydrogen bonding. So there's 3 intermolecular forces from one water molecule to another. 3 forces to break if we are to boil water. So when we are boiling water, we're allowing each individual molecule to float away as a gas by using heat to break the intermolecular forces between the molecules. And that, of course, is going to take a lot more energy to boil water, which boils at 100 degrees, than to boil carbon dioxide, which is already a gas at room temperature. Okay, it's already a gas at room temperature because we've already broken the intermolecular force to allow this to float away, whereas water is a liquid at room temperature because it takes a lot of energy to break 3 forces versus only 1 force in carbon dioxide. Okay, once again, now for ammonia, we have a polar molecule. Okay, so it's in this beautiful trigonal pyramidal shape, remember? Okay, so we have another trigonal pyramidal shape here for another ammonia molecule. Okay, so ammonia is a polar molecule as distinguished by the fact that it's trigonal pyramidal, which means that these 3 polar bonds do not cancel each other out, so therefore it's a polar molecule. So it has the intermolecular force of dispersion forces, yes, because everything has dispersion forces. It has the intermolecular force of dipole-dipole, yes, because that's for polar molecules. They always have dipole-dipole. It also has hydrogen bonding, the 3rd intermolecular force, because hydrogen bonding occurs when we have an oxygen-hydrogen, nitrogen-hydrogen, or fluorine-hydrogen bond, one of those 3. So here we have nitrogen-hydrogen bond, and in water we had oxygen-hydrogen bond. So that's why both of those have hydrogen bonding. So 3 intermolecular forces for ammonia, which means that it's going to take a lot of energy to break those 3 intermolecular forces. And we can predict that ammonia is going to have a relatively high melting and boiling point because it takes a lot of energy to separate these molecules on their own to allow them to float away as a gas. Okay, so this process here, this is used for molecules, so ones that are covalently bonded. Okay, we're not talking about ionic bonding right now, because ionic between a metal and a non-metal, that's an electrostatic attraction, so that's totally different. That's very, very strong when we have an anion and a cation being attracted to each other. Here we're talking about covalent bonds. Okay, so we're talking about molecules. So molecules that are either polar molecules or non-polar molecules. And then we distinguish what intermolecular forces that are present between molecules. And the less intermolecular forces, the lower the melting and boiling point. The more intermolecular forces, the greater the melting and boiling point.